Right, so yesterday we looked at sequences, which is basically a list of numbers separated by commas. Today we're going to start looking at what happens when you take that list and you add up the numbers. We're going to focus mostly on finite series today, which means your number of things you're adding up, it's not infinite. It doesn't go on forever. Okay, so here's the notation that we use to describe a sequence. So this is sequence A. And here's the formula for how we generate the terms. Okay, just to kind of help us out with what we're about to do, let's write out the first few terms in this sequence. Okay, so the first term, let n equal 1. 2 times 1 is 2. 2 minus 1 is 1 squared. Just leave it as 1 squared. If you want to write 1, you can, but I want you to kind of see a pattern here. Okay, next one. James, if I let n equal 2, what's 2 times 2? 4 minus 1? 3 squared. Okay, so that's the next term. 3 squared or 9. Okay, we'll do 2 more. Brianna, what's 2 times 3?
6.
Minus 1? 5. So 5 squared. And without even doing it, anybody think they see what the next term is going to be? James? 7 squared. Okay. So now what we're going to do is we're going to look at adding the numbers up in that sequence. Okay. And the notation we're going to use is a capital S. And the number that's going to take the place of n basically is going to tell us how many terms we want to add up. Do you want to add up just the first term? Do you want to add up the first 2 terms, the first 3 terms? How many terms do you want to add up? Right, so looking at this sequence, the first one basically says you're going to add up the first 1 terms. Okay, so basically just the first term. Okay, so Alex, what's the first term in the sequence above?
1 to the power of 2.
Yeah, 1 squared. Yeah, that's fine. You can just leave it as 1 squared. Okay, now S2 means you're going to add up the first 2 terms to create a sum. So you've got what you had before, 1 squared, plus you're going to add the second term, 3 squared. Okay, so that's S2. Okay, S3. Well, this means you're going to take the first 3 terms and add them up. So you've got the first term, which is 1 squared, second term, 3 squared. Now you're going to add the third term to that, 5 squared. Okay, and we can do S sub whatever number we want. We could add up the first 300 terms if we wanted to. It'd be a little easier if we could come up with a trick or a formula so we don't have to write them all out. Because doing it this way, you'd have to find the first 300 terms and then add them up. Okay, but there might be a faster way to do this. Okay, and then the first n terms. Okay, n would be some fixed positive integer. We don't know what it is, but it would be some positive number. It could be like 10. Right? So you take the first term, the second term, the third term, the fourth term, dot, dot, dot. There'd be a bunch of terms in between. And then finally, the very last term. Well, the very last term would be 2n minus 1 squared, whatever n is. You'd have to fill in for it. Okay, and all of these are called partial sums. All right? So if we had a sequence that did go on forever, and you added up the first 3 terms, you haven't added them all up. You just added up the first 3. Okay, so that's a partial sum. Okay, so these are all what we call partial sums. Okay, each one of the sums we wrote on the other page is a finite series because we only added up a finite number of terms. We're not talking about adding up infinitely many things yet. Again, obviously, to add up infinitely many things, we've got to have a shortcut in there somewhere. Okay, can't add up infinitely many things by hand. It would kind of take a while. Okay, so each sum was called a finite series. Okay, series means you're adding because you had a finite number of terms. We did 1 term, 2 terms, 3 terms. All right, so suppose we had a sequence A sub n. The sequence of partial sums could be written like this. Okay, so basically what we're doing now, if you kind of wrap your head around this, is we're creating a new sequence. And the first term is this in the sequence is S1. Okay? S1 is is the sum of the first 1 terms. The next term in the sequence is S2. This would represent the sum of the first 2 terms. The next term in the sequence would be S3. Okay? So I'll actually do this for the example we just had in a second. Okay, so here we've got a sequence, and each term in the sequence represents a partial sum. And here's how you find partial sums in general. If you want the first partial sum, it's just the first term. Second partial sum, it's the sum of the first 2 terms. Third partial sum, it's the sum of the first 3 terms. And if you wanted the nth partial sum, it's the sum of the first n terms. Okay, so let me put up what we just did. Okay, and let's write out what we have here. Maybe we'll even go to S4 as well. All right, so let's take, I'm basically going to write this for what we have up above. Okay, so S1, it's just 1. S2, 1 plus 9. Okay, Victoria, what's 1 plus 9? 10. That's S2. S3, okay, it's 1 plus 9, which is 10, plus 25. Alex, what's 10 plus 25? 35. And lastly, our fourth partial sum would be 1 squared plus 3 squared plus 5 squared plus 7 squared. So 1 squared plus 3 squared plus 5 squared, that's 35. Plus the next term would be 49. So we get 84. Okay. And then the next one we would add 9 squared, and then 11 squared. And we could keep going. But there's a sequence of partial sums. And why it's handy to do this is if you can find a pattern in these numbers, then you could tell me any partial sum that I wanted to know. So looking at this pattern, if you could figure out what the formula is for this pattern, then you could find the 5th partial sum, the 20th partial sum, any partial sum you wanted without having to add up all the numbers by hand. So if we use, there's actually a website online, it's called OEIS, Online Encyclopedia of Integer Sequences. If you type in the sequence, you got to type in at least 4 or 5 terms. If you don't type in enough, it may give you multiple results. But this should be enough. Okay, so let's just try 110, 35, 84. So let's see if, all right, so we got 1, 10, 35, and 84. Let's hit search. And the next one, let's just check it. So we added 7 squared. The next one, you'd be adding 9 squared. That's exactly what it's showing. 1 squared, 3 squared, 5 squared, 7 squared, adding them up. So here's the formula to do that. It's actually right here. It's n times 4n squared minus 1 divided by 3. Right? So if you wanted to know what the sum of, let's see, what is this really? It's the sum of the first n odd perfect squares. That's what you're adding. The first n odd perfect squares. So if you want to know what the first 20 odd perfect squares add up to, all we'd have to do is plug 20 in for n, and it would tell us without finding each one. Okay? So it's handy if you can find a pattern in a sum of partial sequences. All right, so next thing we're going to look at is what's called sigma notation. Okay? Sigma notation is a shorter way of writing out a sum. Right, so suppose you wanted to add up n terms, and you want to start with the first term. So you put k equals 1 at the bottom. Okay? That's called your index. Okay, your index is where you're starting. The number on top of the summation is where you're stopping. Okay? If n was 7, you'd be adding up the first 7 terms. And then a sub k, that's going to be a formula for your sequence. What's that formula going to be? Could be different in every problem. Okay, so the number on the bottom is where you start. On the top is where you're going to stop. And on the right-hand side here, you're going to have a formula. The formula is going to use the same variable you do on the bottom. Okay, it could be something like 2k plus 1. Okay, so here's an example. Here's a formula that says, in the sequence 2k plus 3, I want you to add up the first 5 terms. That's basically what this says. So the first thing you'd have to do with this notation is you do have to find the 5 terms. This is a shorter way of writing things, but it doesn't actually save you any work. All right, so what I do is let k equal 1, plug it in. 2 times 1 is 2. 2 plus 3 is 5. That's my first term. Okay. I'm going to put a plus sign because I have a summation. I'm adding. Okay. Then you increment k. In other words, you go up by 1. So now let k equal 2 for your second term. 2 times 2 is 4. 4 plus 3 is 7. Now you go up again. You're going to keep adding 1 to k till you finally get to the stopping point. K equals 3. 2 times 3 is 6. 6 plus 3 is 9. Plus k equals 4. 2 times 4 is 8. 8 plus 3 is 11. And lastly, go up one more with k to 5. And that's where we stop. So k is 5. 2 times 5 is 10. 10 plus 3 is 13. And then you'd add all that up. Okay, and I'll write this down in a second, but what we just did is we expanded the sum. On the left is sigma notation. On the right is expanded notation. You've written it out the long way. Okay, so just take the number that's at the bottom, plug that in, and then keep adding 1 to that number until you finally get to the top. These will always be integers, the bottom number and the top number, because they represent terms. Okay, any questions on that? Let's try another one. Let's see, I think I have another one. Let's see. Yeah, we'll do one more in a second. So I already said this to you guys. When you write it with the capital letter sigma, that's called sigma notation. When you write it out the long way, that's expanded notation. So on the test, if you see the directions expand the following sum, I want you to do that and then add it all up. Just add it up. Okay, so let's try this. Expand the sum. Okay, similar to the one we just did, but you know what? So let's change it. Let's make it. It's a little too similar. Let's make it 3k plus 1 squared. Now this time we don't know where to stop. Okay, the stopping point is a variable. So what we're going to do is we'll write out the first term, the second term, the third term, and then we're just going to put dot, dot, dot. And then we'll plug in the last thing in this case, which isn't going to be a number. It's just a letter we'll plug in. Okay, so let's start with k equals 1. Andy, what's 3 times 1?
3.
Plus 1?
4.
Squared?
16.
16. Plus. Okay, Cole, next number, we started with k equals 1. Now we're going to let k equal 2. Plug in 2. 3 times 2 is 6. 6 plus 1, 7 squared, 49. Okay, so we just let k equal 2. Now we're going to go to the next one. Colby, instead of k equal 2, now k will equal 3. 3 times 3 is 9. 9 plus 1 is 10 squared, is 100. Okay, now plus put in dot, dot, dot. We recognize there's a bunch more terms. And now we're finally going to let k equal our last number. James, what's our last number in this case?
3.
Well, what are you going to let k equal for the last number?
N.
N. That's our stopping point, n. So now just fill in n for k, 3n plus 1 squared. Okay. Sigma notation, expanded notation. Questions on that? Now we're going to look at some different properties of summations. Basically how we could take summations and combine them together, how we could split them apart, and a few other things. Okay. I think it's easiest if I just write an example and show you this. Okay, but let A sub n and B sub n be two different sequences. I mean, they could be the same sequence, but they don't have to be. Okay, the idea of rule 1 is what we're doing is we're basically adding up a bunch of stuff, okay? But we're doing it in two different ways. On the left, we're taking the terms in the sequence. We're adding the individual terms together first. The first term in sequence A to the first term in sequence B. Write that down. Second term in sequence A to the second term in sequence B. Write that down. All the way through. And then you're going to take all those results and add them up. Okay, so let's try that. Okay, let's make up a sequence. Very, very simple sequence. In fact, you know what? Let's make it even simpler. A sub k is the sequence 1, 3, 5. B sub k is the sequence 2, 4, 6. Now, if I want to find AK, whoops, let's say A sub k plus B sub k. Okay, all you're going to do is add the corresponding terms together. So 1 plus 2, 3 plus 4, 5 plus 6. Now, I'm going to find the sum. In this case, from 1 to 3. I only have 3 terms. Of what I just did. A sub k plus B sub k. So I'm going to add up all the terms in the sequence right above. So 3 plus 7 plus 11. 3 plus 7 is 10. 10 plus 11, 21. Okay, any questions on what I did there? Okay, now I'm going to do it a little differently, but I should get the same result. On the right-hand side, it says take all the terms in A sub k and add those up first. Okay, so let's do that. So we're going to add up the first 3 terms, the only 3 terms, in A sub k. So we have 1 plus 3 is 4. In fact, you know what? I'll write it up so you can see it. 1 plus 3 is 4, plus 5 is 9. Okay. Now add up the terms in B sub k. Okay, we have 2 plus 4 plus 6. Okay. 2 plus 4 is 6, 6 plus 6 is 12. Okay, now the last step says to take these 2 things and add them together. So we had 9, we had 12. Okay, Brianna, what do you get when you add 9 and 12? 21. Okay, I don't have enough space to write this out again, so I'll just put it down here. When you add 9 and 12, you get 21. So you get the same thing either way. Either add the individual terms together and then add them up, or add all the terms in the first sequence, add all the terms in the second sequence, and then add those up. Same idea works when you change everything to subtraction. If you want to subtract 2 sequences, either subtract all the individual terms, okay, and then add up all the results, or add up all the numbers in the first sequence, add up all the numbers in the second sequence, and just subtract those 2 results. You can do it either way. Okay, and the third rule has to do with multiplying a sequence by a constant. Okay, this one I'll show you. Okay, let's let A sub k be exactly what it was before. 1, 3, 5. Okay, If I want to, let's C equal 2. Okay, we're going to double everything in this sequence. So C times A sub k. Okay, means to take everything in sequence A and multiply it by C. So double it. So this new sequence is going to be 2, 6, 10. Now I'm going to add up everything in that new sequence. So add up the first 3 terms in the sequence I just created. 2 plus 6 gives me 8. 8 plus 10 gives me 18. Okay, so that's one way to do it. I think this is kind of the slow way, because you had to take C and distribute it to every term. Okay, watch what you can do if you do it the way that's on the right. Take your sequence A sub k, 1, 3, 5, and basically do this part first. Just add everything up in your sequence. So we have 1 plus 3 plus 5. Okay, gives me 9. So what I just circled in blue, that result is 9. Take that result and just multiply by C. So now C times the sum from k equals 1 to 3 of A sub k. C is 2. We just figured out this whole sum. It was 9. And 2 times 9, 18. So we get the same answer either way. I think the way on the right's a little faster, because then you don't have to distribute C to every term. You just add everything up and multiply it one time. So those are our basic rules for summations that we're going to use. Okay, and how we can use those rules is to combine this into a single sum. Okay, this first problem is basically, it's like rule 1. You have 2 separate sequences, and you're going to add them together. The key to make this work is you've got to make sure your index and your stopping point are the same. And they are. Okay, they are the same. So we'll write this as a sum from k equals 1 to n. Don't change that. Leave it exactly like it was. Put your first sequence, 5k squared minus 4, plus just put your second sequence. Okay, now combine together anything you can. Okay, Brianna, is there anything I can combine for like terms here? Yep. What do you get when you combine those? 6k squared. James, anything else I can combine?
The -4 and 7.
Yeah, what's -4 and 7? So we're going to do 3, positive 3, and I'm going to put the minus 2k right in the middle. Okay, so there's how you can combine your summations into one. Okay, now, as I said, that's great. It's a short way of writing it. But if you wanted to actually find the sum of the first 50 terms in this sequence, you got to list all 50 out and add them up. It doesn't save you any time. So that's what I'm saying right here. It's a compact way of writing things, but you still have to figure out all the terms you want to add up and then manually add them. Okay, so what we're going to do is next we're going to look at some common patterns, okay? Like adding up the first n integers, okay? Or the first n perfect squares, or even the first n perfect cubes. Okay? So some of these patterns we'll try to figure out by hand. Some of them are a little complicated, so I'll have to help you. All right. So here we're going to write out some partial sums. The first 7 partial sums of the sequence k. Right? So here it's not a very complicated formula. All you're doing is filling in k for whatever the number is, and that's basically the term in the sequence. So the first term is 1, the second term is 2, third term is 3. Okay, and then we're going to add them up. Okay, so my first term, just a 1. Okay, to get my second term, I'm going to have to add what I had before, the first term, plus I'm going to add the second term. Okay, Victoria, if I let k equal 2 and I plug it in on the right-hand side, what do I get?
2.
Yeah, I just get 2. So the first term plus the second term is 3. Okay, third term, or third partial sum. That's my first term plus my second term, plus now we're going to let k equal 3. Alex, what do I get if I let k equal 3 and I plug it in on the right-hand side? I just get 3. So now if we add up the first 3 terms, we get 6. Okay, Andy, now I want to find my fourth partial sum. What's my fourth term in the sequence k?
4.
4. So I'm going to add that onto everything else. So I had 6 plus 4 is 10. Okay, without going through it, does anybody see or think they know what the next term is going to be? Looking at the pattern of the circle numbers. James? 15. Okay, how about the next one? Yep, 21. And the next one? Now, the tricky part, can we find a pattern if we put all those circle numbers in a sequence? Do you see a pattern? Let's see, 1, 3. Well, let's check if it's arithmetic. Cole, am I adding the same number each time? No. So it's not arithmetic. Colby, did I multiply by the same number each time?
No.
No. So it's not geometric. Okay, let me give you a hint at how you can get an idea of what type of pattern it might be. I want you to subtract pairs of numbers that are next to each other. Has anyone ever seen this before? No? All right, let's try it. Brianna, what's 3 minus 1? 2. James, 6 minus 3? 3. Okay, Victoria, 10 minus 6? 4. And then Alex, 15 minus 10? 5. And then 21 minus 15 is 6 and 7. Okay, I want you to do that one more time. Okay, what we're doing is we're finding the differences. Okay. Andy, what's 3 minus 2?
1.
1? How about 4 minus 3?
1.
Okay, I have a hard one for you. What about 5 minus 4? They're all 1. Okay. So we ended up here with a row of constants. Okay. This doesn't tell us what the pattern is, but it tells us what kind of pattern to look for. Okay. How many times did we have to do this process before we got to a row of constants? Cool? We did it twice. Okay. What that means is we're looking for a polynomial pattern with a degree of 2. So in other words, a quadratic. Okay. The formula for this that describes this pattern of numbers is quadratic. All right. If you had a bunch of numbers and you had to do it 3 times before you got a row of constants, you'd be looking for a pattern that's cubic. Okay, the highest exponent would be a 3. Not every this doesn't work for every pattern. If you try this with the Fibonacci numbers, I don't care how many times you keep subtracting, you'll never get a row of constants, ever. And that's because it's not a polynomial pattern. Okay, so this trick only works for polynomial patterns. Now that we know it's polynomial, if you could use your calculator, okay, one way to do it would be go to Stat, go to Edit, and basically type in all of these as coordinates. I'm not going to go through and type it all in, but you could type in the coordinate 1, 1, 2, 3, 3, 6, 4, 10, and so on. And then once you have all your data typed in, you could go to Stat, Calc, and you have to pick what kind of regression, but we already know it's quadratic. based on the trick I showed you. So you could do a quadratic regression, and it would give you the pattern. Okay, just to speed things up a little bit, I'm going to give you the pattern. And don't worry, I'm going to write this down on the next page with a bunch of other patterns. Let's let our position, our n be 4, and see if we get 10. Okay, so 4 plus 1 is 5. 5 times 4 is 20, divided by 2, 10. Okay, let's try the fifth spot. We should get 15. 5 plus 1 is 6, times 5 is 30. 30 divided by 2 is 15. So this is the pattern if you want to add up the first n integers. It's n times n plus 1 over 2. If you distribute it out, that's where you get your quadratic, n squared. Okay, so let's look at that and a couple other patterns. So we're going to look at the one we just did. We're also going to look at adding up the first n perfect squares and the first n perfect cubes. These would be extremely difficult to just guess. You could do them on the calculator pretty easily. By hand, it's a little harder. Okay, let's look at this first one. This one's kind of a weird one. Right? It says you're adding up from 1 to n a constant. This is not a variable. It would be a number. Okay, like sum from k equals 1 to 5 of 3. So there's no spot to plug k in here. The result that you get is always going to be this constant. Doesn't matter what k is. This is always the result, 3. Okay, so let's try it and see what happens. So James, if I plug 1 in here, what's going to be my result? 3. Now I'm going to let k be 2. Alex, if I let k be 2 and I plug it in, what's my result? 3. Now I'm going to let k equal 3. If I plug it in, my result is 3. This is a constant. If I let k equal 4, my result is still 3. If I let k equal 5, that's where I stop. My result is 3. What's a quicker way of doing that? Anybody see a connection between the notation and what we wrote? Yeah?
I was going to say 3 times 5.
Yeah. That's it. All you're really doing is you're adding up the number 3 5 times. Well, the shortcut to that is multiplication. If you're going to add the same number up 5 times, just multiply it by 5. Okay, so that's our trick. If you're going to add up a constant n times, just multiply the constant by n. Okay, the next pattern, this is when you're adding up the first n integers. Okay, so like 1, and then 1 plus 2, 1 plus 2 plus 3, and then 1 plus 2 plus 3 plus 4. That's the pattern. We just went through that. Okay, number 3 would be if you're adding up the first n perfect squares, like 1, then 1 plus 4, then 1 plus 4 plus 9, and then 1 plus 4 plus 9 plus 16, okay, and so on. That's a cubic pattern. If you were to distribute all this out, you'd have n cubed as one of the terms in the top. Well, actually, it'd be 2n cubed. But. Okay, and then the last one, the fourth formula, that's if you're going to add up the first n perfect cubes, like 1, then 1 plus 8, then 1 plus 8 plus 27, and then 1 plus 8 plus 27 plus 64. Okay, all those numbers are your perfect cubes. 1 cubed, 2 cubed, 3 cubed, 4 cubed. Okay, and that's a quartic pattern, okay, or degree 4. So if you distribute out, did everything out here, your highest exponent on n would be a 4. Now we can come up with a pattern for anything you want. You want to add up powers of 4, powers of 5, there's a formula for it. Most likely on a test, we'll stick with adding up perfect squares and below. Okay, so what's nice about these formulas is they basically take something that's written as sigma and change it to a formula. So you can just plug in for n and find whatever answer you want. You don't have to go through and find everything that comes before it. Okay, so let's try that. So in this one, the idea we want to do is we want to break this apart. Okay. Break it apart till we get things that look like one of these four rules. Now, I don't see anything cubed, I don't see anything squared. So I'm not going to have to worry about those rules. But I see a constant, and I see a k. Okay. Degree 1. Okay. Let's just split off the negative 2k and the plus 3 first. So we're going to split it into two summations. The first one is going to be the sum from k equals 1 to n of negative 2k plus the sum from k equals 1 to n of 3. Now this last part we should already know how to deal with. We're adding up a constant n times. We can get rid of that one. The second one, not quite. We've got this negative 2. Okay, we've got a constant in front of the letter. Okay, but I went through an example earlier and I said you can move this constant somewhere. Where can you put this constant instead of right next to the k? Cool? Yeah, we can put it on the outside in front of the sigma. And then we're just going to have a k. It's going to look just like rule 2. So take the negative 2, move it in front. So now we have negative 2 times the sum from k equals 1 to n of k plus the sum from k equals 1 to n of 3. This we have a formula for. So we're basically going to substitute in. Okay. This we have a formula for. So we'll substitute in. Okay, so Alex, what's the sum of k equals 1 to n of k? What's the sum from k equals 1 to n of k? What's the formula for that?
N times n plus 1 over 2.
Yep. So these are things you either have to just memorize or create a reference sheet. Okay. Plus, and now we're going to add up the number 3 n times. Andy, what's a shorter way of doing what I circled in green?
Let's see.
What's our constant here, though?
1.
Well, that's our index. That's just the term we're starting at. But what's the number that we're going to repeatedly add up? 3. We're adding up 3 n times. So what would that be? 3n. Okay, so all this thing in green represents is 3 plus 3 plus 3 plus 3 plus 3 n times. Okay, so that's 3n. Okay, now just do this out. Well, your 2's are going to cancel. So we have negative n squared plus n plus 3n. Distribute out your negative. And combine like terms. Now, if I said to you, I want you to add up the first 500 terms in this sequence. Well, doing it this way, you got to find all 500 and then add them up. Doing it this way, just plug in 500 for n, you do all the arithmetic, and you're done. That's what makes these formulas very, very handy. They convert a summation into a closed formula, closed form. Any questions on that one? Okay, the next one, all I want to do is set it up and kind of show you what you'd have to do. How many summations do you think this one's going to be broken down into? The last one broke down into 2. James?
3.
This one's going to be 3. So you're going to have 2, and then a sum k equals 1 to n of k squared. Then you're going to have a 5, sum k equals 1 to n of k, and then a minus 2. this way. Each one of these you have a formula for. The k squared, the k we just did, and the constant we just did. So this last part's quick. It's just 2n. The thing that's kind of a pain about the k squared one is you have to do this out. So you get n squared plus n times 2n plus 1. So FOIL it out, divide everything by 6. Maybe if you're lucky, the 6 will cancel out somehow, kind of like it did in our problem. The 2 canceled out. Doesn't always work that way, though. In fact, it won't this time because this number is not a 6. And so you do the substitution for all three of those, and then just combine your like terms. All right. Let's take a look at our last thing. Okay, so far the sequences we've been looking at, most of them haven't been arithmetic or geometric. You're not adding the same thing each time. You're not subtracting the same thing each time. You're not multiplying by the same thing each time either. So let's look at what happens if we have a geometric sequence. And we're going to add up all the terms up to a point. Okay, the first, n terms in the sequence. Okay, well here's your first term, a sub 1. To get your second term, you multiply by the common ratio. You'd multiply by r. Whatever a sub 1 is, multiply by r. To get the next term, multiply by r again. A sub 1 r squared. Okay, next term would be a sub 1 r cubed. A sub 1 r to the fourth, all the way up until you get to the nth term. A sub 1 r to the n minus 1. Okay, so let's write this as a partial sum. Okay, so now instead of looking at the sequence, we're going to add everything up. First term plus the second plus the third. Okay, you know what? In fact, I'll even write out a couple more. So a sub 1 r squared, a sub 1 r cubed, and then let's just go to the last term. Any questions on that geometric sequence? Okay, and I'm not going to explain why I'm doing this. You'll see why in a second. I'm going to multiply everything in that sequence, or that summation, by r. Okay, so Colby, what do I get if I multiply this first term by r?
A sub 1 times r.
Yeah, we get a sub 1 times r. That becomes my new first term. Okay, now I'm going to multiply the second term by r. Brianna, what do I get if I multiply this term by r?
A sub 1 r squared.
A sub 1 r squared. James, what do I get if I multiply the third term by r? A sub 1 r cubed. And if I multiply the fourth term, I get a sub 1 r to the fourth. Okay, Victoria, what about my last term? If I multiply a sub 1 r to the n minus 1 by r.
A sub 1
Mm-hmm.
r squared n minus 1.
Okay, not quite. Let's off to the side just write down r to the n minus 1 times r. What exponent is on r but it's invisible? Cool? 1. So the rule when you're trying to multiply things that have the same bases, just add your exponents together. So what happens when you add n minus 1 plus 1? What do you get? Yeah.
N.
Yeah, you just get n. Okay, so that's what you get when you take your your nth partial sum and multiply it by r. Okay, now, the part that gets a little interesting. I want to subtract these two partial sums. I want to take every term in the top, and I want to subtract what's in the bottom. What's going to happen when I do that? You take every term in the top, and you're going to subtract every term that's in the bottom. James?
Won't all the A1s cancel?
So there is going to be something that cancels out. There are a lot of things that cancel out. Let's start with a sub 1. Is a sub 1 going to appear anywhere in the sequence in the bottom? Cool. No. This term doesn't appear anywhere in the bottom sequence. It would have to be before the first term, and it's not there. Okay, let's check a sub 1r. Okay, does that term appear anywhere in the sequence below? Andy?
No.
You don't see an a sub 1r in that bottom sequence?
Oh,
Yeah, so it's there. So what happens when you subtract those two things? Okay, let's check a sub 1r squared. Colby, do you see a sub 1r squared in the sequence below?
Yeah,
Yep, so what happens when you subtract them?
we cancel out.
Those are going to cancel out. A lot of things are going to cancel out here. There's not going to be very much left. Okay, a sub 1r cubed, a sub 1r cubed. Okay, you would also have an a sub 1r to the fourth up here, but it would be in the dot, dot, dot part. So that would cancel out. And what would be the exponent on the term just before a sub 1r to the n? What would be the one that's right before this? In fact, we could even write it in if we want. James?
The a sub 1 part of that and minus 1.
Yep. That would be the term just before that last term. When we subtract them, those are going to cancel out. So you're not left with very much. Okay? All you're left with is a sub 1 minus everything else in the top is gone, everything in the bottom is gone, except a sub 1 r to the n minus 1. Okay, and my goal is to get s sub n by itself. If I can get s sub n by itself, then I'll have a formula for finding the nth partial sum in a geometric sequence. Okay, so what I'm going to do to get it by itself, let's factor out s sub n. That would leave me with a 1 and a minus r. Okay, and then factor out a sub 1 from the other side. And now I just about have s sub n by itself. All I got to do is divide each side by 1 minus r. And that's the formula to add up the first n terms in a geometric sequence. Take the first term, multiply by 1 minus r to the, one small fix. We crossed out n minus 1. The term that's left is r to the n. That's important. Not the n minus 1, that one's gone. It's the r to the n. Okay, so it's a sub 1 times 1 minus r to the n, all over 1 minus r. You don't really need parentheses around the bottom anymore. And I think I have that on the next page too. That's the sum of the first n terms in a geometric sequence. Doesn't work for arithmetic, just geometric. Hey, we don't have to go through the proof again. That was just to kind of show you where the formula comes from. It's actually not too hard if you can understand that idea of things canceling out. Notice here I put the a sub 1 in the numerator. Here I put it in front, bless you, of the whole fraction. That doesn't make a difference. It doesn't make a difference at all. Right, so let's find the 12th partial sum for this geometric sequence. Well, first thing I need to figure out is my first term. Colby, what's my first term here?
2.
Yep, 2. Next thing I should try to figure out is my common ratio. Okay, what I'm multiplying by each time. Anyone see what we're multiplying by each time? James? 1/3. As a hint, r always has to be less than 1. If r was more than 1, these numbers would get bigger and bigger and bigger. And well, I guess for a finite series, you could still add up numbers that are bigger. But when we start to talk about an infinite series, unless the numbers are getting smaller and smaller, they wouldn't add up to anything. Okay, but for a finite series, I guess r could technically be anything. And n, that's how many terms we're adding up. Victoria, how many terms are we adding up?
3.
So did it say find the third partial sum? 12. Adding up the first 12 terms. Okay, enough that it would probably take too long to find the next 9 terms and then enter all those fractions into the calculator. Right, so now just fill into your formula. The 12th partial sum is the first term times 1 minus r to the n. And we know r, so fill that in. So 1 minus r to the n, all over 1 minus r. Hey, let me type that in on the calculator. Okay, I already typed it in. I had to use parentheses just to be careful with what has the exponents, but if you type it in just like that, I also simplified the denominator. 1 minus 1/3 is 2/3. Now, this time, I let the exponent be x. That way I can plug it into the table, and I can find the 12th partial sum, the 10th partial sum, the first partial sum. I can let x be anything I want. Okay, so before we jump to 12, let's just find the first partial sum. Well, it's 2. It's just my first term. Okay, the second partial sum should be 2 plus 2/3, okay, or 2.6 repeating. And it is. The third partial sum would be what you get when you add up those 3 numbers. 2.8, looks like 2.8 repeating. Okay, my fourth partial sum would be if I wrote out the next term and added that in. Okay, my fifth partial sum, sixth partial sum. What's it look like is happening here? James? Is it? No, I think it's always getting bigger. It's definitely still getting bigger. Yeah, it's approaching something. Okay. 2.99, okay, the eighth partial sum, 2.9995. Okay, the ninth partial sum, eventually it's just going to say 3 because it's going to run out of space. But it's not 3. Okay, and finally, if we get to the 12th partial sum, which is what we were looking for, it's basically 3. Okay, it's 2.99999 and then a 4. So this is a good way that you can kind of investigate if you wanted to add up the first 200 numbers. If it's going to approach something within 200 numbers, it would approach it. In fact, the calculator is going to run out of decimals. It would just say 3. Okay, if I type that in. But again, it's approaching 3. right? So this might give you kind of an idea of how an infinite series can actually add up to a number, because each number that you're adding is getting smaller and smaller, so it's making less and less of a difference. Even though you're adding up infinitely many small things. If we were to graph it, you'll definitely see asymptote approaching 3. Keep in mind, though, it doesn't make sense to connect this because we're looking at individual terms. So you almost want to think of it as kind of dots approaching 3. Approaching 3 pretty quickly. By the time you even get to the 4th term, you're already at 2.96. So it's approaching 3 quick. And it'll always be just under 3. Okay, so any questions on that? So again, that's the formula for the sum of a finite geometric sequence. Any questions on anything we did today? All right, so tomorrow we'll talk about a infinite geometric series and a few other terms with sequences. All right, so the homework is on 601. It's 1 to 17 all.